Thank you very much, Andre and Patrick, for inviting me to give this talk. Very glad to stay here. In this presentation, we will talk about the relationship between ISS and integral ISS for time-varying systems. Specifically, we prove that ISS implies integral ISS for various types of systems under suitable hypotheses. We will tell the difficulties we encountered when we try to prove the implication by means of Lyapunov function, how we solve them by using a trajectory-based approach. We also present an extension of an integral ISS characterization to time-varying systems, and we show that this characterization can be extended to axiomatically defined system with inputs. We will start with some basic results, well-known results, in order to put into a context our contribution. We consider time-varying system described by this ordinary differential equation. Here, T is time, X is the state, U is the input. We assume that 0 is an equilibrium point of the systems and that the inputs are locally bounded and measurable. The definitions of ISS and integral ISS are very similar. Both bound the norm of the state at time t by the sum of two terms, one of them depending only on the initial state and time. This term decays to 0 as t goes to infinity because beta is a KL function. A term, a non-negative term, only depending on the input. In the ISS case, we consider the infinity norm of the input, and in the integral ISS case, we consider the integral of a certain functions of the input. We use this norm symbol for the integral, but it is clear that it is not a norm, but for the sake of convenience, we do that. At a first glance, there is no obvious relationship between these stability properties. So to establish the relationship between them is an important theoretical problem. Suppose that B is a locally elliptic function which satisfies this bound. Here, alpha 1 and alpha 2 are k-infinity functions. We say that B is an implication-form ISS Lyapunov function if the derivative of B along the solutions of the systems satisfies this inequality when the state and the input satisfies this another inequality. Roughly speaking, when the state is larger than the input, the derivative of B is negative because the function alpha 3 is a k-infinity function. A dissipation-form ISS Lyapunov function, we say that B is a dissipation form if its derivative satisfies this inequality. Here, this term is negative and depends only on the state, and the other term is non-negative and depends on the input value. Both functions, alpha 3 and rho, are k-infinity functions. B is an integral ISS Lyapunov function if B satisfies a similar inequality than a dissipation-form ISS Lyapunov function, but with the difference that the function alpha 4 is only positive definite when in the ISS case, the function is of class K infinity. It is clear that any dissipation form ISS Lyapunov function, it is an integral ISS Lyapunov function for the system. The existence of an implication or dissipation form ISS Lyapunov function imply that the system is ISS. We have that any dissipation form Lyapunov function is an implication form, but the reciprocal is not true. That is, an implication form Lyapunov function may not be dissipation form Lyapunov function for the system. The existence of an integral ISS Lyapunov functions implies the system is integral ISS. For time-invariant systems, Eduardo Sontag proved that ISS implies integral ISS, assuming the function f is locally Lipschitz in x and u. The proof is heavily based on a converse ISS Lyapunov theorem. In fact, ISS implies the existence of a dissipation form Lyapunov function. So since any dissipation form ISS Lyapunov function is an integral ISS Lyapunov function, the system is also integral ISS. The local Lipschitz condition on XU used in the proof of this theorem is essential because it is used in an essential way in the proof of the converse ISS Lyapunov theorems. So it is not clear how to relax the Lipschitz condition in special for the variable u. For time-invariant case, also it is true that the ISS of the systems implies the existence of an ISS implication form Lyapunov function. This is proved by Edwards, Lin, and Wang in a CDC paper. They assume for this result that the function f is locally Lipschitz in E, X, and U. Note that the theorem asserts the existence of an implication form Lyapunov function, but an implication form Lyapunov function maybe not a dissipation form Lyapunov function, which what we need for proving that ISS implies integral ISS. In the paper of Edwards, we have this example, this scalar example. This system is ISS because x squared is an implication form Lyapunov function. But in this paper, it is proven that this system does not admit any dissipation form ISS Lyapunov function. We prove that this system is indeed not integral ISS. That is, there exists a system that is ISS, but it is not integral ISS. Of course, in the time-invariant case. To see why this system is not integral ISS, we can use these graphics. Here at the bottom, we have the response of the system to unit step inputs for different initial times. Here we are assuming that the initial state is 0. We can see that as larger the initial time is, the faster the state grows and takes a value close to 1 in a very short time. So there exist inputs with arbitrarily small energy, whatever the energy of the input be defined, for which that can provoke a larger excursion of the state. So the system cannot be integral ISS. At this point, we have that there are systems that are ISS but not integral ISS. There are ISS systems that does not admit any dissipation-form Lyapunov functions. So if we want to prove that ISS implies integral ISS for time-invariant systems, we have two paths to follow. One path to follow is to find suitable conditions under which an ISS systems admit a sufficiently regular function B that is a dissipation-form ISS function for the system. And a second path we can follow is to find a method, a trajectory-based method for proving the implication, avoiding the use of Lyapunov function. We have chosen to follow the second approach. We consider families of time-invariant systems in order to obtain a greater generality. Consider this family of time-invariant systems. Here, lambda is a non-empty index set without any additional structures. So capital lambda could be any non-empty set. The index lambda just plays a role of a label for identifying the system in the family. This framework includes a system with parameters in a node set capital lambda, system with perturbation of a certain type, and switch system with switching signals belonging to some prescribed systems. So you obtain some result for this type of this family of systems. This result then can be applied to these types of systems. We say that the family of systems is uniformly ISS or uniformly integral ISS if system of the family is ISS or integral ISS, but with the same bounding function, with the same beta, with the same rho, and with the same ISS gain. The problem we face is to prove for families of time-invariant systems that uniform ISS implies uniform integral ISS. for solving this problem, we have to first find suitable conditions on the function f lambda. Secondly, to extend to time-invariant system and existing characterization of integral ISS. And thirdly, to use a trajectory-based approach in order to avoid the use of Lyapunov functions. We need some definitions in order to establish the integral ISS characterization. We say that the families of systems is zero input, uniformly globally asymptotically stable if for each parameter, for each index lambda, the zero input system is uniformly globally asymptotically stable, but the function beta, which bounds the solution, has to be the same for every member of the family. We say that the family is uniformly bounded energy input bounded state, UBE, VS, if the norm of the states of the solutions of the family of systems can be uniformly bounded by these three terms. The first one depending on the initial state, the second one depending on the energy of the input, and a constant, non-negative constant. In other words, the solutions of the family, the systems in the family are uniformly bounded when the initial states and the energy of the inputs are bounded. The function gamma star, which is assumed k infinity, is the UVE VS gain of the family. For proving our integral ISS characterization, we have to make some assumptions. The first one, it is just for ensuring that the system has solutions. It is a condition, a standard condition for ensuring the existence of solution in an ordinary differential equation. The second condition say that 0 is an equilibrium point for every member of the family. The third condition is a bound, an uniform bound on the functions of the family. Here, n is a non-decreasing function depending only on the state, and gamma is a k infinity function. The function gamma, which will be related later with the integral ISS gain of the system. The fourth condition asks for a kind of uniform continuity of the functions in the family, a uniform condition, uniform continuity in U, but when U is 0. We don't ask the function be uniform continuous in U, but just that the function be uniform continuous in U when U is 0. The last condition say that the functions in the family, when U is 0, has to be locally Lipschitz in X, uniformly in T and lambda. So the solutions of this family of time-varying systems, when the input U is non-zero, could be non-unique. Under these conditions, we can prove that ISS, integral ISS, is equivalent to the zero input uniform globally stability, asymptotic stability of the system, plus the UVVS of the system. This characterization was proved for a single time-invariant system and a more restricted hypothesis in a paper of Angeli, Sontag, and Wang in 2000. There, they assume that the function f is locally Lipschitz in X and U. So our conditions are more general than those assumed in this paper. The proof of this equivalence is trajectory based, so we don't use any Lyapunov function. In the paper of Angeli, Sontag, and Wang, you prove this equivalence by using converse Lyapunov functions and constructing Lyapunov functions for the system. Also, we have that the integral ISS gain can be obtained from the bounds on the functions of lambda and from the UVVS gain. So we can know which is the integral ISS gain if we know the UVVS gain and the gamma function which appears in the bound on the functions f. For proving that ISS implies integral ISS for time-varying systems, we need to assume a stronger hypothesis than those assumed in the characterization of the integral ISS of the system. The first assumption is the same as the same assumption in the characterization. It is just for ensure the existence of ordinary differential equation. The second assumption say that 0 is an equilibrium point of the systems in the family. The third assumption is a kind of uniform continuity in U when U and X belongs to a bounded set, T is greater than 0, and lambda is any index in the family. And finally, the fourth assumption, we assume that the functions in the family are locally Lipschitz in X, uniformly on bounded sets of U, uniformly on T and lambda. So note that we are not asking that the functions in the family be Lipschitz in U. We only require that the functions be locally Lipschitz in the state, but not in the input. We have that if the functions f are Lipschitz in X and U on bounded sets, uniformly in T and lambda, then the conditions D3 and D4 are satisfied. So the assumptions in the theorem of Sontag implies that these assumptions are satisfied. Under these assumptions, we can prove that uniform ISS of the family implies the uniform integral ISS of the family. The structure of the proof is as follows. We have that assumptions D1, D4 implies assumptions C1, C5. Therefore, the characterization of integral ISS holds in this case. That is the zero uniform global asymptotic stability plus the uniform bounded energy input bounded state property is equivalent to the uniform integral ISS of the system. And also we have that under assumptions D1, D2, we can prove that uniform ISS implies that the system is zero UiISS. This is straightforward because this follows from the definition of ISS, but the non-trivial part was proved that uniform ISS implies that the system is uniform bounded energy input bounded state. The proof of this non-trivial part is really involved. It was obtained by Hernán Aimovich after a lot of attempts and required a careful estimation of the difference between the solution X corresponding to an input U and the solution XB corresponding to the same initial condition of X, but considering a truncation of the input U. The truncation is this, and a clever selection of V in order to prove that the difference is small, and from this fact proving that ISS implies that the system is UVEVS. The method we use for proving the implication for families of time-varying systems could be extended to other classes of systems. For example, we can prove that ISS implies integral ISS for families of impulse time system. Families like this. Here, the sequence of impulse time is fixed for every member of the family, but it is not the same if we take different systems in the family. An interesting thing is that in this case, for proving the implication, we need to use a stronger concepts of ISS and integral ISS. These concepts have to include the number of impulse time in the decaying term. So in the decaying term, not only appears time, but also appears the number of impulse times between t0 and time t. Like in the hybrid system theory. The reason for that can be seen in our paper. We also could extend that ISS implies integral ISS in the case of time-varying time delay systems. Here, tau is the maximum admissible delay, and xt is the state history function. The hypotheses we impose in this case were similar to those assuming in the non-delayed time variation case, but here we have to use characterization of integral ISS for axiomatically defined system, which we will present later. What an axiomatically defined system is? Well, an axiomatically defined system consists of a state space. Here, X is the state space. It is a norm vectorial space. A set of admissible inputs U, which is a subset of the functions from the set of non-negative reals to set U. Here U is a norm vectorial space. We ask that the zero input, that is the function that is identically to zero, belongs to the set U, that the set of admissible input be closed by concatenation. That is, if we take two inputs in U and a number T, a positive T, the concatenation of these inputs at T have to be a member of the set of admissible input. Set of admissible inputs are, for example, PHY continuous functions, PHY constant functions, locally bounded and measurable functions, and there are other examples. But for example, the set of continuous functions doesn't satisfy the concatenation property. So this set, the set of a continuous function, is not an admissible set of inputs. The third ingredient in the definition of axiomatically defined systems is a transition map that is a function phi. This is the domain of the function. This is the domain of the function has to be a subset of the set. The function phi depends on 4 arguments. T and S are real. T is greater than S. X is belongs to the state space, and U belongs to the set of admissible inputs. That is, U is a function, not the value of a function. The transition map phi evaluated at T, S, X, U can be interpreted as the state of the system at time T, when the initial time is S, the initial condition is X, and the input is U. So xt defined in this way, and fixing SXU is the trajectory of the system corresponding to the initial time S, the initial state X, and the input U. Here we suppose that the domain of definition of xt is an interval of this form. We say that the triple consisting in the state space, the set of admissible inputs, and the transition map is a system with inputs if this triple satisfies 3 axioms. The identity axiom, the causality axiom, and the semigroup axiom. This axiom, these 3 axioms are satisfied by the transition map of various kinds of systems. For example, system defined by ordinary differential equations, for time delay systems, or for system defined by partial equations, or for semilinear systems. We wanted the number of axioms to be minimal, so we do not suppose any kind of continuity for the function, for the transition map phi. Just we ask the transition map satisfies these 3 axioms. The definition of system we use is inspired in those considered by other authors like as Sontag. In his book, he has a definition of system. For Karafilis and Yang, and recently Mironchenko and Birz. But Mironchenko and Birz define a system, but in the case of time invariant systems, and we are considering time varying ones. Now we will we will give an abstract definition of integral ISS. For an interval I, we define this function, which coincides with u on the interval I, and that it is zero outside this interval. We can see this function as the restriction of u to the interval I. It is not the restriction, but we can see it as the restriction of the input to the interval. We need to define what an admissible integral life functional is. We say that the functional, here we use the norm symbol, again for convenience, but this is a functional, not a norm. This functional assigned to each input in the admissible set of input, non-negative number or infinity. We think of the value of the function at u as the energy of u. This is we see this value as an energy, and we say that this functional is an admissible integral life functional if these conditions are satisfied. The first one is that the restriction of an input to the interval st has to be finite. That is the energy of the restriction of an input to this type of interval has to be finite, and the energy of the restriction of an input to the interval st has to be less than the energy of the input. And the second condition says that if we have an interval T1, T3, and we subdivide this interval in two intervals, into contiguous intervals, T1, T2, T1, T2, T3, and then the energy of the restriction of u to the interval T1, T3 has to be the sum of the energies of the restrictions of u to the subintervals. From these definitions, we have that the energy of the zero input has to be zero. These are examples of admissible integral-like functionals. It is trivial to prove that these two functionals satisfy the condition we impose. We have to extend the definitions of zero uniform global asymptotic stability, of uniform bonding energy input bonding state, and integral ISS to this setting. The extension and straightforward. We had to suppose in the UiISS and in the integral ISS definitions that the system is forward complete, because at this level of generality, it is not true that a bounded solution has to be defined for all t. So we need to impose that every solution of the system is defined for all time t larger than the initial time. In the definitions of the stability property for the system with input, we just replace the integrals by the functionals, as here. For proving the integral ISS characterization, we need to assume that the map phi ensures some continuity property at the zero input, just at the zero input. This is the definition. It is not simply to understand this definition. So I prefer a less formal way to explain what this assumption says. The continuity at zero input is more or less the following. The solution X corresponding to an input can be arbitrarily close to the zero input solution set corresponding to the same initial conditions or any finite interval by reducing the energy of the input. Provide both solutions remain bounded by some constant R. That is, the solution corresponding to an input of very low energy remains close to the solution corresponding to the same initial condition, but to the zero input on intervals of finite length, provided both solution remains in a ball of radius r. We know that this is just a continuity property when the input is zero, and it is a property, is a continuity property with respect to the input just at the point zero. We do not suppose that the transition map is continuous in the initial condition or the initial times, or even in the time t, just at the zero input. And then, assuming the continuity at the zero input of the system, and that the system is forward complete, we can prove that ISS is equivalent to the zero uniform global asymptotically stability of the zero input system, and the uniform bounded energy input bounded state stability. So we can extend the characterization of ISS given originally by Angeli, Sontag and Wang in 2000 for time-invariant systems, to a general class of system defined by means of axioms. As an application of this characterization, we can obtain this characterization for semilinear system. Suppose we have the semilinear system here. T is greater than 0. The state belongs to a Banach space. The input take values in a norm vector space, in norm vectorial space. A is a densely defined linear operator that generates a strongly continuous semigroup. F is PXY continuous in T and continuous in XU. We suppose that the function f is Lipschitz in X on bounded sets of U and X uniformly in T. We also assume that the function f satisfies this bound for all T, this uniform bound in T. Here again, n is a non-decreasing function, gamma is a k-infinity function, and the last hypothesis is that the function f is uniformly continuous at u equals 0 on bounded sets for x. Under these conditions, an acceleration we are considering for the semilinear system a weak solution, that is the solutions of integral equation. And then we can prove that 0 UiISS plus UBEVS is equivalent to integral ISS semilinear systems by assuming that the set of admissible input is that of the PSY continuous functions U, and that the function is this integral, and also we assume that the system is forward complete, and under this hypothesis we can prove the characterization of ISS. The proof is based on the fact that the semilinear system satisfies the axioms, and that the assumptions on F ensure that the semilinear system enjoys the continuity at the zero input property that we commented before. Some conclusions. We have shown that there exists time-varying ISS systems that are not integral ISS systems. we have extend an existing characterization of integral ISS to axiomatically defined systems. We have proved that ISS implies integral ISS for various types of time-varying systems under suitable hypotheses. Our method is trajectory-based and avoids the use of Lyapunov functions. Okay, that's all. Thank you very much for your attention.